Welcome to Bot Thoughts by Soft. I'm Alex, and with me is Sam. Today we're getting into multi-agent orchestration, because as soon as people move from one LLM call to a system with multiple agents working together, things get complicated fast. Sam, what's driving this push toward multi-agent systems in the first place?
A few converging forces. First, context window limits. Even with a million token context, there are tasks so large and complex that one agent can't hold everything in mind at once. A financial analysis agent that needs to read 10,000 quarterly reports can't do that in a single pass. Second, parallelism. Some tasks are naturally parallel. If you're building a software feature, one agent can write the implementation while another writes tests, and a third reviews for security issues. Third, specialization. You get better results when agents are fine-tuned or prompted for specific domains rather than one generalist agent trying to do everything.
What are the main architectural patterns that have emerged? Because every time I read about multi-agent systems, I see terms like orchestrator-worker, supervisor, swarm. It's a bit of a zoo.
Let me give you the 4 patterns that actually matter in production. First, orchestrator-worker. One central orchestrator agent receives the goal, breaks it into subtasks, dispatches them to specialist worker agents, collects results, and assembles the final output. This is the most common pattern and the one you should default to. Second, pipeline agents are arranged sequentially. Each one's output feeds the next, like an assembly line. Great for document processing workflows where you extract, then classify, then summarize, then route. Third, supervisor with critics. A primary agent does the work, and one or more critic agents review the output and flag issues. The supervisor either revises or passes to the next stage. This is extremely powerful for improving output quality. Fourth, swarm or peer-to-peer agents communicate directly with each other. There's no central coordinator. This is the hardest to reason about and debug, and I'd avoid it until the other patterns have failed you.
When you look at the frameworks for building these, LangGraph, CrewAI AutoGen, OpenAI's Swarm, how do they map onto those patterns?
LangGraph is the most flexible. It models agent workflows as directed graphs where nodes are agents or functions and edges represent control flow. It supports all 4 patterns and is the best choice if you need fine-grained control over state management and routing logic. It's lower level, though more code to write. CrewAI is higher level and opinionated. You define agents with roles and backstories, and a crew that coordinates them. Great for getting started quickly with orchestrator-worker or pipeline patterns. AutoGen from Microsoft is powerful for conversational multi-agent systems where agents collaborate through a shared chat. OpenAI's Swarm is the newest. It's intentionally lightweight, focused on handoff patterns where one agent transfers control to another. For production systems handling real data and real failures, I lean toward LangGraph because of the control it gives you.
Let's talk about state management, because this is where I've seen teams get into trouble. How do you keep track of what each agent knows and what the system has done so far?
State management is genuinely the hardest part of multi-agent systems. You have 3 categories of state. First, conversational state, the message history within a single agent interaction. This is easy, it's just a list of messages. Second, task state, the progress on the overall goal, what subtasks are complete, what results have been returned, what's still pending. This needs to be persisted somewhere, a database, a key value store, or a graph like LangGraph's built-in state graph. Third, shared memory, facts, documents, or artifacts that multiple agents need to access. This is usually handled through a shared vector store that all agents can query. The failure mode I see most often is teams treating multi-agent state like single-agent state. They put everything in the context window of the orchestrator and run out of space or lose coherence after a few iterations.
What happens when an agent fails in the middle of a multi-agent workflow? If worker 3 of 5 crashes, does the whole thing fall apart?
It depends entirely on whether you designed for it. Naive implementations absolutely do collapse. If the orchestrator is just awaiting all workers and one throws an exception, you either get a partial result or a full failure. Robust systems need a few things. First, checkpointing persist state after each agent step so you can resume from the last successful point rather than starting over. Lang graph has this built in. Second, retry logic with exponential backoff. Transient failures from API rate limits or network timeouts are extremely common. Third, fallback strategies. If a specialized worker fails, can a generalist agent do a lower quality version of the same task rather than blocking entirely? Fourth, timeout handling. Agents in production systems must have hard time limits. An agent that loops indefinitely is worse than one that fails fast.
Multi-agent systems multiply the number of LLM calls. How do you manage cost when you might have 5 or 10 agents all making API calls?
Cost is the thing that surprises teams most in production. A single user request that feels simple might fan out into 15 LLM calls across multiple agents. 3 strategies. First, right-size each agent, use cheaper, faster models for simple routing or extraction tasks, and reserve expensive frontier models for the complex reasoning steps. GPT-4o Mini for classification, Claude Haiku for summarization, Claude Opus only for the final synthesis that actually matters. Second, cache aggressively. Agents in a workflow often make similar queries. Semantic caching with a vector store catches queries that are equivalent even when not identical. Third, parallelize where possible. If 3 agents can run simultaneously rather than sequentially, your wall clock time and cost per request both improve. Profile your workflows and identify bottlenecks before optimizing.
How do you debug a multi-agent system when something goes wrong and you have 10 agents all doing things in parallel or sequence? That sounds like a debugging nightmare.
It is a debugging nightmare without the right tooling. Distributed tracing is non-negotiable. Every agent call, tool invocation, and handoff needs a trace ID and a span. Langfuse and Phoenix from Arise are purpose-built for LLM observability and both support multi-agent tracing. You need to be able to answer. What did the orchestrator send to Agent 3? What did Agent 3 do with it? What did it return? How long did it take? And how many tokens did it use? Log the full input and output of each agent step, not summaries, the actual content. And run integration tests with recorded agent responses so you can replay workflows deterministically when debugging a specific failure path.
Give me a real-world example of a multi-agent system working well in production.
Customer support automation is the clearest example right now. Here's a common architecture that I've seen work well. An intake agent receives the customer message and classifies the intent, billing issue, technical problem, account question, feature request. It routes to a specialist agent based on classification. The specialist agent looks up the customer record, queries a knowledge base via RAG, and drafts a response. A quality agent reviews the draft, checks that it's accurate, not hallucinating, and matches the company's tone. If it passes, it's sent. If not, it goes back for revision. The whole pipeline runs in 2 to 4 seconds for most queries. The intake and quality agents use fast, cheap models. Only the specialist agent uses a frontier model. Cost per query is around 2 cents. That's a real production system handling tens of thousands of queries per day.
What are the anti-patterns? What do teams get wrong most often when they first build multi-agent systems?
4 big ones. First, over-engineering. Teams reach for multi-agent systems when a single well-prompted agent with good tools would work fine. Don't add agents. Add agents when you have a specific reason to. Second, agents that are too general. Each agent should have a narrow, well-defined responsibility. An agent that does everything is just a worse version of a single agent. Third, no human-in-the-loop checkpoints. Fully autonomous multi-agent systems for high-stakes tasks without any human review gate are dangerous. The agent that confidently executes the wrong plan in 10 steps is worse than the one that fails on step 1. Fourth, forgetting about rate limits. When you have 10 agents all hammering the same API simultaneously, you will hit rate limits immediately. Design your orchestration layer to manage concurrency and queue requests intelligently.
Let's wrap up. Key takeaways. The 4 patterns are Orchestrator-worker, pipeline, supervisor with critics, and swarm start with Orchestrator-worker. State management is the hardest part. Use proper persistence. Design for failures with checkpointing and retry logic. right-size models to manage cost, and observability with distributed tracing is not optional. Sam, what should listeners do this week?
If you haven't used LangGraph yet, spend 2 hours working through their tutorial. They have excellent documentation and the getting started examples are realistic. If you're already building agents, look at your cost per request and trace the breakdown. 9 times out of 10, there's one expensive call that dominates and a cheaper model would do just as well. And look at LangFuse if you're not already tracing your agent calls. It's free for self-hosting and will transform your debugging experience.
That's Bot Thoughts. If you got value from this episode, subscribe on YouTube and Spotify. We put out new episodes every week. And if you'd like to support the show, you can buy us a coffee at buymecoffee.com/amticsoft. We'll see you next episode.